Salutations, dear viewers. I welcome you to Busy Little Minds, a place where all curious minds can quench their thirst for learning. Today is a special day because I am announcing my first ever series in this channel, titled Basic Physics. This series is as simple as it sounds, the basics of physics that any beginner should know. A crash course, if you will. So sit back, grab some popcorn, and don't forget your notebook, and get ready to be mesmerized in the world of physics. Today, I will regale you with tales of motion, forces, and Newton's laws of motion. This may be boring, but we must start at the basics. Things will start getting interesting soon. Firstly, let me explain forces and net force, because the concept of a force is something you absolutely need to know. A force is any correspondence that can change the motion of an object. A force is required to change the motion of an object, can set an object in motion, can change the speed and direction of motion, always has magnitude, size, and direction, measured in newtons. Net force is best described as the combination of all forces exerted on an object. I'll explain net force in detail as we go along the slides, but hang tight for now. Now, let's discuss Newton's laws of motion. Sir Isaac Newton, the author of Principia Mathematica, is also the famous scientist who discovered gravity. He also made 3 basic laws of motion that are still considered the base of physics today. The unit that is used to measure force, the Newton, is also named after him. Newton's first law states that an object in motion will stay in motion and an object at rest will stay at rest, unless any force is used upon the other. This law is also sometimes called the law of inertia. It is called the law of inertia because inertia is matter's resistance to change its motion. So, Newton is basically saying that if matter is moving, it won't stop moving, and if it's not moving, it'll stay stationary. There is an exception to this rule, of course, because after you exert a force on matter, it can change its current state. If you want a drink of water, you exert a force on the glass to pick it up. If you want to stop a soccer ball from getting into the goal, you stop it by exerting a force on it so it stops moving. The second law pronounces that the acceleration of an object is equal to the net force on the object divided by the mass of the object. As we learned in the last slide, net force is the total amount of force acting on an object. So, the second law is actually saying that acceleration is equal to the net force divided by the mass, or net force is equal to mass times acceleration. This is shortened to F equals ma, where F is for force, m is for mass, and a is for acceleration. The third and final law declares that forces act in pairs. For every action, there is an equal and opposite reaction. This may not seem obvious in everyday life, but think of a slingshot. If you want to launch a stone in a slingshot, you pull it backwards. Why? Because, as Newton's law states, every action has an equal and opposite reaction. If you hold a slingshot back, then let it go, it goes in the opposite direction of your pull. The stone goes flying forwards, not backwards. This proves that every action, indeed, does have an equal and opposite reaction. Finally, this is the additional information, equations, and terminology you need to know before going on to the next episode. 1m equals 1 kg times 1 meter divided by s squared. This may seem like a foreign language at first, but you can decipher it if you know what the units mean. The n here stands for newtons, the unit that's used to measure force. Kg stands for kilograms, a unit used to measure mass. M stands for meters, and s squared stands for seconds squared. This text is saying that a newton is described as the force necessary to move 1 kilogram by 1 meter per second squared. If you don't know what that means, don't worry. 1 meter per second squared is a term that describes acceleration. A certain object can be accelerated to a speed of 1 meter per second in the time span of 1 second. 1 newton is the force required to accelerate an object that weighs 1 kilogram to this speed. When net force is in the same direction as the velocity, then the object will speed up. When the net force is in the opposite direction as the velocity, the object will slow down. This text can be likened to the soccer ball example I gave in the previous slide. When a soccer ball is hurtling towards you and you want to make it stop, then you have to apply force in the opposite direction. This will make it slow down or stop. If you want to make it go faster, then you have to apply force in the same direction, which will make it speed up. Velocity is speed in a certain direction. Let's go back to the soccer ball example. Let's say that you're kicking the soccer ball at the top of a hill. It goes straight for a while, maintaining a constant speed. The speed and velocity are both constant in this case, but then a sudden breeze knocks it off its course. The speed remains constant, but the velocity has changed. Velocity changes when an object changes direction or speed, while speed changes only when an object speeds up or slows down. Momentum equals mass times velocity. Momentum is a tricky concept to describe because it is often confused with speed or acceleration. Momentum can be thought of as energy. The best way to describe it is through an example. Let's imagine that you have 2 marbles. One marble is 2 ounces and the other marble is 6 ounces. You decide to do a marble race with a friend. Now you just have to pick your marble. Which marble will go faster? On one hand, the smaller marble is appealing because since it's small, it will accelerate faster, right? Well, not quite. Since momentum is mass times velocity, the more the mass or velocity, the faster the object accelerates. The only way to increase the velocity in this case would be to make the ramp steeper, and that's not possible because both ramps need to have the same steepness to be a fair race. So, the only way to ensure your win is to increase the mass. The larger marble might take longer to accelerate due to its mass, but its top speed would be much faster than the top speed of the smaller marble. Speed equals change in distance over change in time. Basically, you can say that the speed of an object is determined by the distance and the time it took to travel that distance. If you ran 15 kilometers in an hour, your speed would be 15 kilometers per hour. Motion is relative. If you think about it, this makes sense. Our perception of motion depends on what we compare it to. For example, if you compared an Olympic runner to a normal person, the normal person would be considered slow, of course. But if you compared a normal person to a snail, the normal person would be considered fast. Average speed equals total distance x has traveled over total time x has traveled. This also makes sense because in math, the average is the sum of the numbers divided by how many numbers are being averaged. So it makes sense for average speed to be the total distance over the total time. Acceleration equals final velocity minus initial velocity over time. Acceleration is another tricky topic, but since you know what velocity is, you'll find it easier in comparison to learn about acceleration. Acceleration is similar to velocity, except that it has an added quantity, time. Velocity only has direction and speed, but acceleration has direction, speed, and time. Instantaneous speed is equal to the speed of x at any given moment. Instant speed is different from average speed. The speed of an object is not always constant. It can vary. The instant speed is the speed at a certain moment. Motion is the change of position. The simplest definition that we have learned so far. Motion. If you move your hand to swat a fly, that's motion. Even the act of breathing is motion, because you are changing your position in space. Conservation of momentum. The amount of momentum before and after a reaction or collision is the same. This principle is similar to the conservation of matter. After you boil water, you may not be able to see it anymore, but the amount of water stays the same, just in a different state. Let's say that you kick a soccer ball into a wall. The ball may stop moving, and this is not because the momentum has vanished. Energy never can be destroyed. It is because the momentum has been transferred to the wall and the floor. The wall does not move because it has absorbed the momentum, and neither does the floor because it has also absorbed the momentum. If you enjoyed this video and learned something new, give it a like. If you want to be notified when the next episode comes out, subscribe. Thanks so much for watching, and see you next time.